Okay, we start up. If my microphone works. Yes, it does. I think. Yeah. The only hole that we had in the weekly schedule will be then Wednesday before lunch, Thursday after lunch. The rooms, I'm not sure. I think we have to be here on Wednesdays. Wednesday is always a terrible day. Experts in team steal all small rooms, so it's impossible. But I mean, it's possible for us to survive here, so that should be okay. Thursdays, at least this week, I got a room, but this might change. So pay attention to his learning, and I'll post it here as soon as I have next week's schedule. But in generally, it will be then Wednesday before lunch, Thursdays after lunch.
This means at 1, 2, 3 or 23?
It's called Kjell, KJL, and that is the Kjellhus building just across the street over here. And they have some small rooms. For you guys, the student schedules should be here. Did I not hear? Here. So it should fit okay here for actually all of you, at least those of you who were here last week. Thursday, we will have one of you that's missing a lecture. But a lot of you are going to be away anyway, so hence the video. So I'll post them on YouTube. I'll put links on its learning so you can find it here. And the quality is actually quite okay. You should be able to hear my voice quite loud. You should be able to see the blackboard and screen quite well. What you don't get is your own voices. So whenever anybody here asks a question, I have to repeat it for the camera, so don't think I'm retarded or something. I just have to do it, okay? Any administrative questions from you before we begin? So roughly, if possible, 6 hours each week. And that should keep us quite on track to be finished before Easter. Absolutely. If we can keep this pace, I'm not sure. Sometimes I have some exercises on Thursdays. I have to be away, but maybe then for half an hour or something, then we have to take a break or something. We'll find out. You have been given some material. So this is sort of the basic book that I'm going to use, following the chapters more or less. Here, just copies of some old slides that I've been using. So we start, as you can see, with a good bunch of finite difference problems. And remember, this course is divided. One part, finite difference, and that's the basics. All of you have to know that. Then afterwards we will specialize. So then you can choose on the exam if you want to focus on finite volume, on structured measures, if you want to focus on fast solvers, pure numerics, or if you want to focus on turbulence and turbulence modeling. So today I will start with the finite difference, and no, I don't have it here, do I? Yes, I have it. So, for finite difference, a rough layout of my plan. So, starting today, with the basic equations, how we can derive them, how we can classify them, and also start looking into finite differences, different notations, stuff like that. As a first example, sort of a little project, we look into unsteady flows, focusing on here the Struhol number. And also, as a first example, how we can solve the Navier-Stokes sort of quick and dirty. The projection method, and here I then have an old program that I like to play around with. It's called the SOLA algorithm, stands for solution algorithm, a very old one from 75 something, and developed at Los Alamos. It's the shortest Navier-Stokes solver I've been able to find, so the source code is 1 page, and it's MATLAB, so you can play around with it as you like. It's not fast, but pretty funny. And we can illustrate a lot of different problems that we arrive when they arises, especially here when it comes to stability. Stability is sort of a crucial point in CFD, so that one we have to discuss a little bit. So that should be the beginning of this course. Yeah, I'll list in some references here if you like. Also on its learning you'll find reference material. So I just copied a couple of classical books as PDFs that I found. Numerical heat transfer and fluid flow by Patankar, sort of an old Bible when it comes to finite volume. It's very old, quite thin, very expensive, and he only wrote one version of it. It's never been updated, so it's full of errors. So don't buy it, but it's easy to read, sort of straightforward. He was a very practical guy. He wanted a solution. He was an engineer. He didn't care about, say, fancy numerics and stuff. He just wanted an answer. And in those days we didn't have heavy computers, so okay, we had to cheat a lot. So that's sort of a nice beginning if you want to have a peek into the way of thinking to create a finite volume code. Learner, I haven't studied this book this much, but it looked okay, at least at first glance. Also this one. You find several free books on the internet if you search, so I just stole a couple. So I assume these are illegal. That means also the first one. That means I'm not allowed to give these files to you. So if anybody goes to jail, it's going to be me. If you find a file somewhere, then you can take it. That's allowed according to Norwegian law. But you're not allowed to give it to other people. But I mean, it's learning, so it should be an internal page. So I'm not too worried. The last one here, this one is free actually. This one is legal. It's a very short little book by Briggs, how to deal with multigrid, which we will address when we come to fast solvers. So that is what you have here so far. Little info sheet we looked at last time, and that's it. So we start with the Navier-Stokes, and we start by deriving them. See if this one works. Yes. So I like to switch a little bit in between using the whiteboard, using the computer, running some demonstrations. So we switch. I like to switch a little bit. A little bit writing is okay, I think. Prevent you from falling asleep too often. So we start with the basics. Basic equation. Basic equations based on, say, physical principles. we have conservation of mass. Then we have Newton's second law of motion, which a lot of people refer to as conservation of momentum. I don't like that. The momentum is not conserved at all. The change of momentum equals mass times acceleration. So it's sort of a momentum budget or something like that. But here I would say, call it the momentum equations. And finally, conservation of energy. In this course, I'm going to focus on the two first ones, almost solely. The last one, energy, you don't actually need it unless you are dealing with compressible flows. Then you have to deal with the temperature and density changes, so on. So I'm roughly focusing on incompressible flows in this course. Now, how to derive the different equations? You have a choice, and you choose between integral or differential form. Integral, differential. And then you can also choose between something that is called conservative versus non-conservative. This concept with conservative, it's sort of an invention by the CFD people. It doesn't mean that the conservative form conserves mass, energy, anything better than the non-conservative form. So it's just a name for different ideas how you derive the basic equations. So conservative, both the integral and the differential forms, they will be fixed in space. So here you are looking sort of at a large region, an area, a control volume, something. But it's fixed in space, meaning the flow will go straight through it. So here you have the flow, and here you have then the your control volume with a control surface CS. CV and CS, I'm going to use that. If you want to do the conservative form, differential, you do the same, but then of course you have a tiny little delta X, delta Y fluid element, which is then fixed in space, and the flow goes straight through. So here it's fixed in space, both of them. Non-conservative, they are moving with the flow, but you still have then here a large control volume, but now the volume itself is moving. So these faces, the surface then follows the flow. And same goes then with a tiny little element. He is then moving with the flow. Moving with the flow. So that will be your choice, one of these four. Now you might argue that it really doesn't matter. You can pick either of them, and mathematically you can start with one and then mathematically manipulate it a little bit, some algebra, and then you can derive the others. Of course, it should be the same equation, just in different versions of it. True, but there is an argument behind all this, so just try to follow me here. I have to take a little sidetrack. something that we need later about the divergence. Physically, what does it mean, divergence? So we start sort of with this one. We have a CV following the flow. CV following the flow. So we can say here we have our control volume, and this one now is moving with the flow, meaning the mass inside here is fixed. Fixed mass inside. So it will always be inside. And now take a small little surface element, a little ds, and say he's now going to move in the flow direction, which might be somewhere here, for instance. But here we have a surface vector, then perpendicular on ds. So if we now look at the change of this volume, during a time, say delta t, okay, then we have to look at the velocity dot normal vector. He will now give us the velocity perpendicular to a surface. So the transport of the surface will sort of be in this direction. And if you multiply this one with ds, then we have now velocity times a little area, and if you multiply with a certain time, we have a volume. So now the volume ds will be spanned out, you might say, in this direction, like a small volume like this. And then, of course, we have to take the entire control volume with the total control surface, meaning we have to take a surface integral. Of course we have, of the entire control surface. So this is the change of the volume during little time. And now I want to have the time rate of the change of my control volume. How does he move? How does he behave? Hence, we are going to need the total derivative. Large D's, so there we also include these convective terms. And what do we take the derivative of? The volume. So volume, I use V, large V with shoulders. That's a volume instead of velocity, just an ordinary V. So how can we write this? Well, this is the change during delta t. So now I want the time rate, hence we take 1 over delta t, and then the same integral, like that. Cs, so of course delta t will fall, and it's actually only the velocity that we are left with inside here. Now remember, this surface integral, that's a closed surface integral. You take the entire surface around your volume. So delta t drops, and of course here you can now use the divergence theorem and say that this surface integral of, say, the flux out of your surface equals the volume integral of the divergence, the volume of the entire control volume. So this now, change of a volume, how he moves, well, the volume integral of the divergence. Just so you can recall it, if you want to write this one out as an operator, you have the time derivative, and then you will have velocity vector dot with the nabla operator, and then operating on something. Here it's the volume that you put in, time derivative, and here the convective terms, something like that. Now say this volume V, volume becomes very, very small. So we say volume goes to be a small delta volume, and then the volume, the control volume I'm going to integrate over, is so small that, okay, the divergence, of course, then will be constant inside the volume. So divergence, roughly constant. So then we can rewrite this equation as the following. The divergence, no, sorry, the total derivative, substantial derivative of a small volume equals, and what do we get here? You'll have the divergence multiplied with, and then you're just left with the volume integral, which is of course just the volume itself, like that. Or if you like, this is normally the way you find this, divergence equals, and then 1 over this volume, and then total derivative of the volume, small volume. Here we have it. If you want an image of divergence, sort of a more physical, what does it mean? If you have a region in space, x, y, and then you start putting some passive markers uniformly distributed in space. Now let those markers join the flow for a little time. How will this picture look, say, after delta t? Well, that depends on the flow. So we can have this image, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this region that I started with, he changes the form, and here also he changed size. Okay, this means the divergence is going to be positive. He expands. And if you have the opposite, yes, those 9 points, they move, but they become quite a small area. Okay, the divergence will be negative. If the divergence is 0, then this change of the volume is 0. You keep the volume. So the concept of divergence-free flow is also called, say, a volume conserved flow. You keep the volume. Any volume will be the same in time. You can't compress it, you can't expand it, incompressible flow. Any questions to that one. Now, let us try to, oh, this is going to be bad. Ooh. Don't we have some remedy here? Let's try to derive the different equations, starting with mass, choosing the 4 different concepts, different ideas, the different starting points. Looks like I've gotten some permanent markers. No, it says whiteboard marker. Okay. When you derive the different equations, you should, of course, keep track of your assumptions during the derivation. What assumptions do we need to take? Hopefully not too many. I mean, the fewer the better. So what we really like is some universal laws that will be true no matter what. So if we now take continuity, conservation of mass, and then we try the 4 different versions of this derivation and see what we get. So I just write it like here. We have 4 different versions. Let's start then with this one. So it's an integral formulation and it's conservative. How do we think? You keep a region fixed in space, your control volume. So then you will say the following. Net flow, say of mass, of course, out of your control volume, out of CV through your control surface, CS, equals the change inside. And that then has to be a time rate of the decay or the disease. No, not the disease, decrease. Disease is something bad. We don't kill mass here, we just move it around. Decrease of mass inside your control volume. Of course, this is the basic principle. Leonardo da Vinci, I think he formulated something like this. Mathematically, you just now set up directly surface integral of, and then you need the density, and then the velocity perpendicular to the surface, ds. There you have kilo per second out of your controlled surface, equals minus. It's a decrease inside if you have a net out. Why out? Well, always the normal vector points out of any volume. That's the standard conversion. Always out. Hence, if this one is positive, we are losing something. So negative inside time rate of, and then we need all the mass that we have inside our control volume. Okay, that then has to be a volume integral of my density, the volume. So that will be my continuity equation on integral form. What about if I choose the non-conservative form? What then? I choose this version. Well, that one should be easier, shouldn't it? Because you start out with one control volume, and the mass that you have inside must then equal same volume integral, control volume of the density dV, which is constant, of course, because my control volume is moving with the flow, so he doesn't change. And moving with the flow means you use the total derivative. Then you are moving with the flow. Total derivative of this volume integral, rho d volume, or a control volume like this. This change has to be 0. And yes, it is the same equation, but you see you need a little algebra to get there. It's possible, yes, but why do it? I mean, it's the same equation, yes, but a little bit different philosophy behind it. Let's have a look at the other one, differential form. So we start with a little element fixed in space. I mean, this is the standard way that we do it in the basic courses. You start out with differential equations. So you look at here a small little element, dx, dy, and dz if you want. And then you look at the flow of the flux of mass in and out. If you only look at in the x direction, you say to the left there for this little element, I have a velocity in the x direction, small u, and then we multiply with the density, and then we multiply with the area that he is penetrating here. So rho u, I take it as a sort of a average value here on the center point to the left on this surface. And what do you get on the other side? Well, you have the same plus a possible change in both velocity and density when you have moved the distance delta x. So you have to take a possible change in account, meaning we need an x derivative of the quantity rho u multiplied with the distance we have been going. And as you know, you can't remove delta x here, partial derivative. No, that's not sort of a physical distance in meters the same way as a pure differential. So no, you can't skip it, since they are changing with more than one variable in general, of course. So if you look at net outflow, here only in the x direction, what do we get? You have something entering. Well, he will then be negative, so that will be minus, and then we had rho u multiplied with the surface. That should now be dy and dz. That has to be the case. So this is the amount of kilo per second entering from or exiting from the left, Then for the right, positive. And then we have sort of the same rho u here and the same surface, but I have something in addition, plus ddx rho u dx, and also this one should now be multiplied with dy dz, the surface here. So that's the net outflow. And of course, the quantity itself doesn't matter. If it's constant, then you have zero net flux of mass in or out. It's the change. It's this one that is important. And yes, you get the x derivative and then multiply it with dx, dy, dz, meaning you multiply with the entire volume. And then you do the same in all directions. So then you say net outflow in total will then be ddx rho u ddy rho v, velocity in the y direction, and dz rho w, velocity in the z direction. And all of them will be multiplied with dx, dy, dz, small little volume. So that's net outflow. And then we sort of have to think in the same way as we did here, equals time rate of the decrease inside. If you have a net outflow, then you're going to lose something on the inside, which then will read minus change of the density multiplied with the same little volume, dx, dy, dz. So you treat the density as constant inside one single little element, one density inside. And then of course you skip the volume, and you have the equation saying change of the density in time plus, and then the square brackets becomes the divergence of rho velocity vector. So here you have the standard classical differential continuity equation, now taken on a conservative form, as we say it. Any questions to that one? That's okay. This is classic stuff. What about the last one? I want this one, moving with the flow. It should be the same equation, of course, but a little different. So we have a little lump, small little element, and inside here we have a lump of mass. So mass, a little delta m, will now be equal to, and since it's a differential little element, I can write it as a density multiplied with a small volume, delta volume, like that. And of course I now demand for a small little element moving with the flow, this one has to be constant. Of course. So the differential equation covering continuity would just be the time rate of this quantity has to be 0. Rho small little volume equal to 0. And then we expand this one, the chain rule. So here we will now have a little volume, and then the derivative of the density, d rho dt, and then the other way around, density, and then the derivative of the little volume, the volume dt. That's just the chain rule. Should equal to 0. And then we rewrite this a little bit. I mean, we have 0 on the other side. Take the derivative, no, not the derivative. Multiply the equation with 1 over the volume. Then I have this one alone, d rho dt. And then what do we get here? Well, you have the density, and then you have 1 over volume multiplied with this guy, which is exactly what we have here. So you have this one now multiplied with the divergence of the velocity equal to 0. So this sort of an alternative version of this one. Same equation, you get the same answer, you might think, using either version. And of course here, if you now write it out term by term, you will see, yes, they are the same actually. So what was the point of all this? Why should we do all 4 of them? As I said, it's enough with 1, as we normally do it in the basic course, starting with this one, and then we take the volume integral of this equation to get the different integral forms of the same equation. That's normally the way we do it. That is not the way you should do it. And the reason is the following. What have we assumed before we started here? Well, as soon as you play around with derivatives, you also say the quantity you are looking at has to be a continuous function. It must be possible to create derivatives. Not so with integrals. So the integral form, they can handle sudden jump, shock waves, whatever, inside the volume. That's allowed. I mean, for this guy here, and then the velocity, or density, or whatever, that's okay. He can behave whatever he wants. So the integral form covers more physics than the differential. Differential, you say everything has to be continuous functions, or else you can't create derivatives. So if you have a choice, of course you will choose the integral form. And for you guys dealing with CFD, either master or PhD level, you have to say we are going to use a CFD code. All CFD codes, more or less, is going to be based on some integral formulation of your basic equations. Then you don't start with the differential forms. A lot of people do that. They say, okay, the basic equations, mass, momentum, energy, they will be some differential, partial differential equations. They start there. And then they say, I'm using an integral code, hence I take the volume integral of these equations to come up with the form that actually the code is using. Don't do that, because when you start with differential form, you say, I have to have continuous functions. But the code that you are actually using, integral form, he doesn't say that. So don't start on differential form unless you are really have to. When we now are going to start with the finite difference codes, we are going to use differential form and create numerical versions of all our derivatives. Then we have to start with the differential form, of course. We have to use that one. But in general, the CFD code is going to be an integral form. Then start with the integral equations directly. Don't start with the differential forms. So here, now we have done all 4 versions with the mass. You can do the same with momentum. You can do it with energy. It's going to be a lot of work, so I'll leave that as an exercise. So that was my point. Don't use differential form unless you have to, unless you really mean it. And the reason, yeah, we can say a little about it. The integral form is more fundamental. It covers more physics. Covers more physics. For example, a shock, then you have the density. He can behave maybe something like this, a sudden jump, and then another value. And of course, you can't create a derivative in the vicinity of this shock. It's not possible. But doing an integral of the density, where you have this sudden jump somewhere inside your volume, that's quite okay. Not a problem. Of course, what you can do is using not just the density, use the density multiplied with the velocity. That one together will actually be a more continuous function. So you can work your way around this. Same goes with the pressure through a shock. Typically, he will drop all of a sudden. Again, impossible to make derivatives there. But instead of just looking at the pressure, you can look at the pressure plus and then the dynamic part of it, rho u square, or 1/2 if you like. That will now also be more continuous functions. Finally, we have something also that you should be aware of. Well, first of all, be aware that different authors might mean different things when you talk about conservative, non-conservative form. Also, you have something called a strong form versus a weak form. And people may put different things in this concept, what they actually mean with it. Normally, they say a strong form, you will have derivatives, spatial derivatives, in front of them. So you will have it on the form say ddx of something on the outside. ddx, ddy, dz or something. Weak form, then you will have something here and then multiplied with derivative and then something else inside. The strong form there is neat when you look at a surface or a volume integral afterwards. Sort of more easy to handle fluxes in and out. So when you write it on this form, it's easier than to sort of translate your equations into an integral form where you have better control of what is entering or exiting your surfaces. Here, an integral of a derivative, then they disappear and you are left with whatever is here. If you take an integral here, then you have to calculate the integral as it is. See the difference? So, but these words, strong and weak, people are using them a little differently. So be aware, be aware. Any questions? Then we make some coffee.